So in this video, we're gonna be going over the derivative as the rate of change, but it as an application of derivatives. So first thing we're gonna do is we're going to recall what the definition of position, velocity, and acceleration is. Position is where the object is at a time t, and is denoted by s of t. And velocity is basically the derivative of the position function, and it represents the speed with direction, and it represents the change in position. So there's a starting point, there's an ending point. So there is going to be change in between the starting and ending point, and that's denoted as delta t. The acceleration is the change in velocity, just like how velocity is the derivative of the position function and represents the change in position. Acceleration is the derivative of the velocity function and represents the change in velocity. And it can be denoted as either a of t, or it could be denoted as the derivative of the velocity function, or it could be denoted as the second derivative of the position function. And another important concept in rate of change and derivatives is the topic this upcoming thing I'm going to talk about, which says that if the acceleration function is in the same direction, meaning it's either positive or negative, and it's the same as the velocity function, the object will speed up. That means that it's basically saying that if at a certain time the acceleration function and the velocity function have the same not the same values but the same signs, so they're both positive, either they're both positive or they're both negative, then the object is actually speeding up in space. But if one is positive and one is negative, or in this case they're in opposite directions, the object is actually slowing down. And we're going to actually apply this to two problems. One is just going to be a basic problem, introducing you how to actually approach these kinds of problems. And then we're going to apply this to a real life problem involving bacteria. So this is the first problem. So at t seconds, we have this position function. We're given this position function, and we want to determine when it's speeding up and when it's slowing down. So the first thing we're going to have to do is actually determine what the position function is, velocity function is, and the acceleration function is. So the position function, we are given that. So that's let's see, that is t cubed minus 3t squared minus 45t plus 7. That's what we're given. Now, the velocity function, as we know, is the derivative of the position function. So all we really need to do is just take the derivative of the position function. So the derivative of t cubed is 3t squared. Derivative of negative 3t squared is negative 6t. Derivative of negative 45t is just negative 45. And the derivative of this constant 7 is just 0. So we don't need to really write that. We should already know that. So that's v of t, or velocity. Now the acceleration function, as we know, is the derivative of the velocity function. So the derivative of 3t squared is just 6t. The derivative of negative 6t is just negative 6. And the derivative of negative 45 is just 0, since it's a constant. We don't really need to write that because, once again, we should already know that. Now, as we said before, we need to determine where the velocity function and the acceleration function are the same signs in order to determine if it's either speeding up. And then we need to determine where they're at different signs in order to determine where they're slowing down. So now that we have the velocity and acceleration functions, we need to basically simplify this whole process by factoring each of these functions in order to make a little coordinate plane and pick points to compare the velocity and the acceleration function. So first we're going to find the roots for each of these functions, and this is just simple algebra. So let's factor the velocity function first. We factor out the 3, we get t squared minus 2t minus 15, and we factor this again. We factor this into its roots, which is just t minus 5 and t plus 3, which is just t is equal to 5, t is equal to negative 3. And we can, in this case, we can ignore the negative 3 root. We don't really need that since we already have the 5. Now, the acceleration function, we can factor out the 6. We get t minus 1. That means that t here, the root here is just 1. And for the velocity function, we could include the negative 3, since when we're looking at speed is equal to the absolute value of the velocity. So even if we have the negative here, we can it'll just become a positive when we're calculating the speed. So what I'm going to do is just do exactly that. I'm going to use all these roots and make a little coordinate plane, and then we can start comparing the velocity function and the acceleration function. So I'm going to start this coordinate plane from 0, this number line from 0, and the first root I'm going to put down is 1. Second one is I'm going to put down is 3, and then 5, and this is going to be approaching infinity. So what we're going to do is first find the points for the velocity function. So first we're gonna have to pick the same points when we're comparing the acceleration and velocity. So let's just pick the points first, and then we just plug them into each of those functions. So in between 0 and 1, we can pick 1. A value we can pick is 1/2. In between 1 and 3, a value we can pick is 2. In between 3 and 5, a value we can pick is 4. And in between 5 and infinity, we can pick any value, so we're just going to pick a simple one, which is 6. So we have to evaluate the velocity function at each of these points, and all we really need is the sign to determine if it's speeding up, and we just need the sign so we can compare it to the acceleration function. So when we plug in 1/2 for the velocity function, so let me calculate this out real quick. So when we evaluate 1/2 in the velocity function, we get negative 47.25. So that means there is a negative value here in between 0 and 1 for the velocity function. Now when we evaluate this function at 2, we once again get a negative number. We get another negative number. We get negative 45. So we can just write negative sign. We don't really need to write the number. We just need the sign so we can compare it. And then when we evaluate this at 4, the value of 4, we get negative 1. I mean, we get negative 21, so we get another negative value. So this is, we get another negative value. And when we evaluate this at 6, when we evaluate this at 6, we get a positive value of 27. So from 0 to 5, the velocity function is negative. So that means it's either going down or it's going towards the left. So from 0 to 5, it's all the way negative. Now, for the acceleration function now, same process. We use the same values, and we find this we find the values and the signs at that certain point for the acceleration function. So when we plug in for the acceleration function, that we plug in 1/2. When we plug in 1/2, we get -3. So in between 0 and 1, the acceleration function is negative. So when we plug in 2, we get a positive value of 6, positive 6. So it's positive in between 1 and 3. Then when we plug in 4, we get another positive value. We get a positive value of 18, positive 18, between 3 and 5. And from 5 to infinity, when we plug in 6 into the acceleration function, we get another positive value of positive 30. So from 0 to 1, the acceleration function is negative, and from 1 to 6, 1 to infinity, the acceleration function is positive. So now, this is where we start comparing. So now we see that in between 0, the only areas where the sign are different for the velocity function and the acceleration function are in between 1 and 5. It's in between 1 and 5. So the way we write this is with inequalities. So we're going to write, let me move this around a little. So now we're going to write that. So now that we know the signs of each of these values, of the functions at each of these values, we can now start comparing them using the statement we said before. So when a of t, when the acceleration function and the velocity function are the same sign, the object is speeding up. When they're in their opposite signs, they're slowing down. So from 0 to 1, the acceleration function and the velocity function are the same sign. So from 0 to 1, acceleration function and the velocity function are the same sign. And we're using open brackets because 0 and 1 are roots of those certain functions. So we're not going to be including those. We're just going to be including what's in between the domain. So from 0 to 1, they're both negative, so they're speeding up in between that. And so this symbol right here means and. In between 5 and infinity, the acceleration function and the velocity function are positive, so they're both speeding up. So 5 to infinity, they're both speeding up. So in between these intervals, the object is speeding up. And in between 1 and 3 and 3 and 5, the signs are different. Acceleration is positive, velocity is negative. But we can make this interval a little smaller, so we don't have to make it such a big not such a big interval, but so many little pieces of the same interval. We can just say the interval is 1 to 5. So in between 1 to 5, once again open brackets because they're roots. In between 1 and 5, the object is actually slowing down since they're opposite signs. And that's basically it. That's the answer. So for this position function right here, in between the time 0, meaning the starting point, to time t equals 1, and time t equals 5 to time t equals infinity, the object is actually speeding up. And in between the interval time t equals 1 to time t equals 5, the object is slowing down. Now moving on to a second question about bacteria and real life application. Let me write down the question. A bacteria is growing according to the function so this is going to be the position function. Just remember that f of x is equal to x cubed minus 18x squared plus 96x plus 20, and t is in hours. T is going to be in hours. And the question to answer is, when is the population of this bacteria growing and shrinking? Growing and shrinking means the same thing as speeding up and slowing down. Growing correlates with speeding up. Shrinking correlates with slowing down. So we're gonna apply the same method we used before, but we're gonna apply this to a real life problem of bacteria. So first things first, identify the acceleration function. Identify the acceleration function. Identify the velocity, and we already know the position function right here. So all we need to do is find the velocity and the acceleration function, and then once again pick points and compare. So first things first, the velocity function is just the derivative of the, let me actually make this s of t, since we're going to be using t. So v of t is equal to the derivative of the position function. So the derivative of t cubed is just 3t squared. Derivative of negative 18t squared is just negative 36t. The derivative of 96t is just 96. The derivative of 20, which is a constant, is just 0, so we don't need to write that. Now the acceleration function is the derivative of the velocity function, and that's going to be the derivative of 3t squared is just 6t. The derivative of negative 36t is just negative 36. And then derivative of 96 is just a constant, so it's going to be 0. Derivative is going to be 0. So now we have the velocity function and the acceleration function. Next step we did was factor these functions. So for velocity function, we're going to factor 3 squared minus 12t 12t plus 32. Now when we factor this, we get t minus 8, t minus 4. Now we have the values t equals 8, t equals 4. Those are the roots of the velocity function. We do the same thing for the acceleration function. Factor out the 6, we get t minus 6. We get a root of t equals 6. So now we have 3 roots. Now we can make that coordinate plane and continue on basically we can continue on comparing the velocity and acceleration functions. So when we make the coordinate plane, we start from 4, 6, and then we have 8, 4, 6, 8. Now we pick points and evaluate them in the velocity function and the acceleration function. We just need so recall that we just need the signs, and we just need to compare them with each other. So if the signs of acceleration and velocity are the same, the population is growing. If the signs of acceleration and velocity are different, the population is shrinking. So we're gonna pick values in between 4 and 6. We can pick 5. In between 6 and 8, we can pick 7. In between 8 and infinity, we can just pick 9. Or we can just pick 10. 10 is a lot easier. So v of t. Now we plug in 5. So when we plug in 5, so when we plug in 5 for v of t, we get a value of -9. So there's going to be a negative value for velocity here. When we plug in 5 for the acceleration function, 30 minus 36, so it's going to be a negative value, -6, so it's going to be negative again. So in between 4 and 6, they're both the same sign. So now when we plug in 7, so let me plug that in. When we plug in 7, once again we get a negative value for the velocity. We get -9. So we just plug that in. And then we plug in 10 into the velocity function. We get a positive number, positive 36. And when we plug in 7 for into the acceleration function, we get positive 6, so positive value. And when we plug in 10 into the acceleration function, 60 minus 36 is just 24. So positive 24, so it's going to be positive value for acceleration at t equals 10. So now we compare, now we just compare what we basically got, well, the data we just got. So from 4 to 6, from values 4 to 6, so actually we should add t equals 0 as well as the starting point. So we'll just pick 1 right here. We'll pick the values 1 right here, and then we start comparing again. So the velocity function at 1 is just equal to the velocity function is positive here at 1, and the acceleration function is negative at 1. So first thing we're going to do now, what we're going to do is compare acceleration and velocity at these certain intervals. So in between 0 and 4, our function is the population is actually shrinking. So in between 0 and 4, the population is shrinking, since the signs of acceleration and the signs of velocity are different. And in between 6 and 8, in between times 6 and 8, the velocity is also shrinking because the signs are different for acceleration and velocity. 6 and 8. So these are the intervals where the population is shrinking for the bacterial colony. And in terms of where the population is growing, is going to be in between intervals time t equals 4 to times t equals 6, because both signs are negative for acceleration and velocity. The function is the function shows that the population is growing in between this interval, and the population is increasing from time t equals 8 to infinity. So after times t equals 8, the bacteria colony keeps on growing from 8 to infinity. Population is growing. And that's the final answer. Those are just the values. So this problem is asking, when is the population growing and shrinking? The population is shrinking between intervals 0, 4 and 6, 8. And this is time. And the population is growing in between t equals 4 and t equals 6. And t equals 8 and t equals infinity.